Open round neighborhood of radius r, center of x is this set of all y and p such that the distance from y to x is less than r. And I can make an example of this in let's say r to the n. So if we let v equal r to the n, then the open ball centered on x with radius r is just the set Pr of x equal to set of vectors y in R to the n such that y1 minus y squared plus yn minus n squared is this squared. And so, for example, in this example, all points inside a, or let's just say n equals 2, all points inside a circle of radius r forms an open ball in R squared. Okay. By the way, this occurs to me. There was a question asked at the end of last lecture about vertical meaning 1 to 1 and on 2, whether I meant and on 2 or I did in fact mean or on 2 because I was talking about the finite dimensional vector space, and in a finite dimensional vector space, on 2 and 1 to 1 are the same thing. But in an infinite dimensional vector space, like for example, the right-shift operator that we were using in the example, it's no longer the case. And then for a general operator, it has to be and. Only in a finite dimensional case is or sufficient. Okay. Right, so a bounded subset then a bounded subset of a normed vector space is some subset that can be enclosed in an open ball of finite radius. Bounded subset of a normed vector space starting very big or so use ink. Okay, so about a subset of a non-vector space is a subset that can be enclosed in an open ball. Key point is that it has a finite radius. So if you want to anchor to some intuition, Any region that you can draw on a piece of paper is a bounded subset of R2. Since I can always find a sufficiently large circle that will enclose that piece of paper. Or that regional piece of paper. Okay? Okay. So now suppose I've got some subset of a known vector space. I'm going to call that subset open if each of its points, each of the points in that subset has an open round neighborhood that lies entirely in that subset. Okay. So a subset, or rather, an open subset O of